Have you ever wondered why your hands feel warm when you hold them near a burning candle? That comforting heat isn't magic, it's science in action. Let's break this down. Enthalpy, symbol H, is simply the total heat content of a system when the pressure stays constant. Whenever a chemical reaction happens, the reactants turn into products and the heat content shifts. The difference between the enthalpy of the products and that of the reactants? That's called the enthalpy change of reaction, or RH. Let's put it into words. Delta RH equals the sum of enthalpies of products minus the sum of enthalpies of reactants. You can also express it like this. Delta RH equals sigma of A I multiplied by HM of products minus sigma of B I multiplied by HM of reactants. Here, AI and BI are just the number of moles in your balanced chemical equation. This formula is your key to understanding how much energy moves during a reaction. So what does the sign of RH tell us? If RH is negative, the reaction releases heat, making it exothermic. Think of a campfire or burning fuel. If RH is positive, the reaction absorbs heat, making it endothermic. That's like ice melting on your palm. Let's see a classic example. When hydrogen gas reacts with oxygen to form water, the reaction is H2 gas plus half O2 gas gives H2O liquid. Here, RH equals minus 285.8 kilojoules per mole. That negative sign means heat flows out to the surroundings. Now, you might be thinking, why should I care about enthalpy in real life? Well, enthalpy changes power everything around us. The fuel in your car engine combusts and releases energy to spin the wheels. Cooking gas heats your food through exothermic reactions. Even your own body uses enthalpy when digesting food. In industries, knowing RH helps engineers control temperatures safely. Imagine producing ammonia in a huge reactor. If you ignore the heat released, things could literally blow up. Understanding enthalpy isn't just for exams, it's essential knowledge for designing safe, efficient processes. Alright, let's solve a real example together, step by step. Problem: calculate the enthalpy change for this reaction. N2O4 gas plus 3CO gas gives N2O gas plus 3CO2 gas. Given enthalpies of formation times N2O4 plus 9.7 kilojoules per mole times CO minus 110 kilojoules per mole times N2O plus 81 kilojoules per mole times CO2 minus 393 kilojoules per mole. Step 1. Add up the enthalpy of products. 81 plus 3 times minus 393 equals 81 minus 1179, giving minus 1098 kilojoules. Step 2. Add up the enthalpy of reactants. 9.7 plus 3 times minus 110 equals 9.7 minus 330, giving minus 320.3 kilojoules. Step 3. Subtract reactants from products. Delta RH equals minus 1098 minus bracket minus 320.3. This simplifies to minus 1098 plus 320.3 equals minus 777.7 kilojoules. Answer: the enthalpy change for this reaction is minus 777.7 kilojoules per mole, strongly exothermic. One more thing. When comparing enthalpy changes, it's important to use standard conditions. Substances are pure. Pressure is 1 bar. Temperature is 298 Kelvin, which is 25 degrees Celsius. When you see a little circle after H, like RH degree, it means you're dealing with standard enthalpy change. This keeps measurements consistent and reliable. Let's wrap up what you've learned. Enthalpy change of reaction, or RH, tells you how much heat is exchanged during a chemical reaction. A negative RH means heat is released, A positive RH means heat is absorbed. You calculate RH by subtracting the enthalpy of reactants from that of products, considering their moles. So next time you light a match or cook a meal, remember, you're witnessing enthalpy change in action. Thanks for learning with me. In our next video, we'll explore Hess's law, a powerful tool for calculating enthalpy indirectly. See you there.